This is Richard Ignis of the Department of Physics and Astronomy at East Tennessee State University. I'm going to talk about Kepler's third law. Kepler's third law deals with the idea of the relationship between how large an orbit is and how long it takes for an object to get around the sun. What we usually have is a situation that looks like this. We have some orbit. This is a top-down view of that orbit. The sun would be out of focus. Remember that the sun is located along the major axis. And this is the orbit of some body around the sun. Could be a planet, could be an asteroid, a dwarf planet, might be a comet, could even be a grain of dust, if you will. Right now we're just going to have it be a planet. Some planet, could be anybody, Neptune, Saturn, the Earth. And the idea is that there is a relationship expressed in Kepler's third law between the orbital period and the size of the orbit in terms of the semi-major axis. Remember that the full distance along the long length of the elliptical orbit is twice the semi-major axis. So A is the semi-major axis, semi referring to half the distance. Then the time for an object, such as this planet, to get all the way around its orbit, one full time, is the period, for which we'll use the symbol P. So that's the orbital period. Now when you're talking about orbits around the sun specifically, Kepler's third law is P squared is A cubed. For this to work, we need certain kinds of units. The A here is in astronomical units. The P is in years. So we can use this equation either way. Given the semi-major axis in astronomical units, we can use the relationship to find how long it takes for the orbital period, or given the orbital period in years, we can figure out how large the orbit is in terms of its semi-major axis. Let's go ahead and do some examples. First example, suppose we have the period. Suppose the period is 8 years. The question is how large is the orbit? What we do is we have P squared, square the period, that's 8 squared, that's 64. Then Kepler's third law says that A cubed is equal to P squared. So A cubed equals 64. To get A, we have to take the cube root of both sides. Write a cube root this way. It's one way to write the cube root. Another way is to use powers. It turns out that roots are fractional powers, so 1/3 or 0.3333 and so on. So this is A. Now the cube root of 64, we can do that without a calculator. It turns out that's 4. 4 times 4 times 4 again is 64. It's 4 times 4 is 16, and then 4 16ths make 64. So the answer here is 4. Since the period was provided in years, the answer for the semi-major axis is astronomical units. Let's try another one. This time, the known is going to be the semi-major axis. We want to find the period. Suppose that the semi-major axis is equal to 5 astronomical units. The question is, what's the period? So the rule is P squared equals A cubed. We're going to have to cube A. That's going to be 5 cubed. That's 5 times 5 times 5. So 5 times 5 is 25, and 5 quarters makes a buck and a quarter. So that's 125. Now, we know that p squared equals a cubed. So p squared equals 125. To isolate the p by itself, we need the square root. What we do to one side, we have to do to the other side. So p is equal to the square root of 125. 125 is not a perfect square. We would need to use a calculator to get the correct answer. However, it turns out 11 squared is 121, which is pretty darn close. So the period is just a little over 11 years. So we're going to put approximately 11 years. Let's try an example where we need a calculator. Calculator example. For this case, I'm going to assume a value for the period. Suppose that we have an orbit that's equal to 17.3 years. And what we want to know is the semi-major axis. So we're going to have to square that to use Kepler's third law. So that's 17.3 squared. Okay, going to need a calculator for that one. Most calculators have a square button on them. 17.3. You can also use an internet browser like a Google or Yahoo. You should be able to put 17.3 squared in there and get an answer as well. I can square 17.3, get 299.29. I'm just going to put 299 down. Don't need all those digits. So that's p squared. Now a cubed is equal to p squared. So a cubed is 299. We're going to have to take the cube root. So a is equal to the cube root of 299. Now in my case, my scientific calculator has a cube root. I just have to hit the shift button, and the cube root is this after hitting the shift. So if I put 299, shift in the cube root function, I get 6.68688, a whole bunch of digits here, which is about 6.7. So that'd be 6.7 astronomical units. Not every scientific calculator has a cube root function. A different way to do it would be to take the 299 and use the x to the y button. If I hit that, the 299 would be the x. After hitting that button, I need to enter the power. In this case, the cube root is a 1/3. So I can put 0.3333, make that a digital value. 1/3 is 0.333. Just put a bunch of threes in there. You can hit the x to the y button again. That enters the y as the power. Or you can hit the equal sign. I'll hit x to the y. Get the same value, 6.686, and so on. So the answer here is 6.7, and that's in astronomical units because the period was provided in years. Let's do another calculator example where this time we know the semi-major axis and we want to find the orbital period. So here, the A is 109.8 astronomical units. This is really far out in the solar system. Not as far out as the Oort cloud, where dormant comets are located, but this is more than twice as far out as the orbit of Pluto. We are finding more and more objects out at that distance. Some of them dwarf planets or objects that may one day be classified as dwarf planets. So suppose we have something out at over 100 astronomical units away from the sun. How long does it take for that object to get around the sun one time? We want to use p squared equals a cubed. We're going to have to cube this value. Again, my calculator has a cube function as well as a cube root. If I put 109.8 cube functions here, I have to hit shift in the function. That's this very large number. I'm going to write down scientific notation. But again, if you don't have a cube button, 109.8, you can put that in an internet browser and cube it. Or you may be able to use this X to the Y button. In this case, we just put 3, since we're cubing, not cube root. I'm going to hit the equal sign in this case. I get the same number. This is a very large number. I'm going to use scientific notation. I have past the decimal point 1, 2, 3, 4, 5, 6 spots. So this is 1.32 times 10 to the 6. Now p squared equals a cubed. So to get the period, I'm going to take the square root of this. 1.32 times 10 to the 6 square root. So 1.32. For scientific notation, some calculators will have an EXP button. Others may have an EE button. So in my case, EXP, I get these digits up here indicating a power to enter. I put the 6 there. For the square root, I have to hit shift. There's the square root function. And I get a number 1,148.9125 and so on. So basically 1,150 years. Just over a millennium. That's how long it would take for an object at this distance from the sun, semi-major axis, to go around the sun one time. One of the things that's very interesting about Kepler's third law is that if I had a circle that was the 109.8, about 110, if I had a circle that was 110 astronomical units, it would take a little over 1,000 years for this to go around the sun. But if instead it were an ellipse, so that the semi-major axis, which is half the distance, was 110 astronomical units. So it's not a circle at all, but is an ellipse. Well, it would still take the same amount of time to get around that orbit, the 1,150 years. The interesting thing about Kepler's third law is it doesn't care about the eccentricity. The shape of the orbit is not relevant, only the size of the orbit in terms of its semi-major axis.